Zoom. Right. Yeah. Yeah. Okay, so welcome back to the class. So we were discussing about the AC applied to the inductor. That's what we were discussing. So we will continue from there. AC applied to the inductor. What happens that we will continue, we'll finish that AC chapter theory first, then we will go for some questions based on that one. Okay, so here we were discussing about AC applied to the inductor, and we finally reached to this inductive reactance. We got XL is equal to omega L, that is the inductive reactance, and this graph also we discussed. Here the main point is in an inductor, the voltage leads and the current lags. Okay, or we can say, okay, that's enough. Voltage leads and the current lags, and there is a phase difference between phase difference of pi by 2 or 90-degree phase difference is there between the current and voltage in the case of an inductor. That's what we done at the last. Now, here we discussed about this phase difference. Now, this is not over actually. That somebody's mic is on. Once you mute your mic. Mute the mic. Those who kept the mic on, please mute it. YouTube. What happened? Board is not visible. I can start the camera. Okay, now can start. I can start the camera. Start the camera. Okay. Okay, so we'll continue. So in the previous one, we stopped here. So here we had a phase difference that we discussed, and this XL is called as inductive reactance. And see here, we have to discuss more about this inductive reactance that we will do later. That is, we have to see this point. XL is equal to omega L we are getting. So we can see that when this frequency or the omega increases, this XL also, the opposition also increases. So if you draw a graph for that one, how you will get, if here is omega or the normal frequency is here, XL is here. So when this one increases, that also will increase. Okay, so you'll get a graph like this. So when we study for capacitor, inductor, resistor, everything together, we'll discuss about that in detail. But you should know that this opposition increases when the frequency increases. So what is the meaning of that one? For lower frequency, or DC can pass through this one, and when the frequency increases, the opposition also increases. So this is the graph between the opposition and the frequency. If you take the graph between current and the frequency, it will come opposite because it will reduce. So that we will discuss later, because that is an important point. Now what we have to do is we have to discuss about the power. That is, when you connect an inductor in a circuit, how much power will be dissipated. When we connect a resistor, the power is, or the heat produced is I square RT, like that we have some heat is produced or some power is there in that, and heat produced and heat by time, that is power. So we have to discuss about the power in the case of our this inductor also. So first we will discuss about the instantaneous power. That is, at a particular instant or for a fraction of time, how much power will be dissipated. So you see here, the power across the inductor PL is given by I into V. So for always power, we will use the same equation, I into V. So what is I here? I is Im sine omega t minus pi by 2. So we know it is always behind by an angle of pi by 2. And now we have to multiply with V. So what is V here? V is Vm sine omega t. Now, when you take this one, you can write this one as this Im sine omega t minus pi by 2 can be taken as Im cos omega t or minus Im cos omega t. So it is minus Im into Vm cos omega t into sine omega t, like that we can write. Now here this one also we can again simplify. This is sine omega t and cos omega t is coming. Is actually, if sine 2 theta expansion, like that, if you take this one, if you compare with the trigonometric identity, you can get it as minus Im into Vm by 2 sine 2 omega t, like that we can take. So this is the instantaneous power across the inductor. But we have to take the average power, because instantaneous power is for a small instant. We have to take the average of this one. So to calculate the average power, we can take the average power as the average of this one. So when you take the average of this one, these constants we can take outside, minus Im Vm by 2 into this average of sine 2 omega t. Now, if you take this one, you are multiplying this quantity with this quantity. So what about this quantity? This is the average of sine theta. Sine omega t means it's a theta, and when t changes, it will go for the full cycle. So for the full cycle, when you take sine theta, its average, this value will become 0. So the total effect of this one is the power across the inductor, the average power across the inductor will be 0. That is a very, very, very important point here. That is, in the case of resistor, when we connect a resistor in a circuit, there is some power dissipation across the resistor. When current is passing through the circuit, some power dissipation will be there. But in the case of inductor, it is not like that. That is, if you connect an inductor in a circuit, so this inductor is having an opposition that we already discussed now, this one, XL and all. So what happens? This one is making an opposition in AC, or it is helping us to reduce the AC current through the circuit. But there is no power dissipation across this one. So without any energy loss or without any power loss, this inductor, or when it is used for reducing the current, we will call it as choke also. So this inductor will reduce the current through that one without energy loss. You can use the same for the same purpose. We can use a resistor also. In an AC circuit also we can use a resistor. When you use the resistor, what happens? The current will be reduced. But when you use a resistor to reduce the current, the extra energy what we are reducing, that will be converting it as heat. But here you can see the power dissipated across the inductor is 0. That is very, very important point. So once more we will sum up about this inductor. So we discussed about the inductor. So inductor, the current and voltage are in out of phase by an angle of pi by 2, and the voltage was leading and the current was lagging. That is, the voltage is going front and the current is behind by an angle of pi by 2, and the opposition is given by omega L, which is called as XL, all the inductive reactance, which is equal to omega L. Or we can say that when the frequency is very less, or when it is like DC, it can pass through that one without any opposition. When the frequency increases, when it becomes more and more AC, so that time it blocks. So it is actually blocking AC, and it is allowing DC to pass through that one. So that's how we can think the inductor will allow DC to pass through that one, and it will block AC. Now afterwards, we discussed about the power dissipated across the inductor, and across the inductor we have a power dissipation which is equal to 0. So there is no power dissipation across inductor. So inductor is a good way to reduce current in the AC circuit without power loss. So that's the important thing. Inductor can be used to reduce the current in an AC circuit without power loss. We can use resistor also. When you use the resistor, there will be a power loss. So that's about this inductor. Now we will move to the AC voltage applied to the capacitor. Here also the concept, everything is same, only we have to think about when AC voltage is applied to a capacitor, what is happening. So here you see the circuit diagram is same, only here we have a source of AC here, and we have a capacitor connected here, and here also we are not marking the direction of the current at all, because it's AC deviates here, or it's the positive and negative changes continuously. Now here also we have to apply the Kirchhoff rules. So when you apply Kirchhoff rule here, what you will get? The source voltage is Vm sine omega t minus Q by C is equal to, that is the voltage across this one will be, capacitor will be Q by C. So or you can write this equal to Q by C, because voltage across capacitor is Q by C, which you studied in the this second chapter. You already studied that one. Voltage across capacitor is Q by C. Now see here, we have to calculate the current from this one. So how we can get current from this one? What is the relation between this charge and current? That is I is equal to dq by dt. So if you want to calculate dq by dt, we have to rearrange this one for q first. So the q is actually Vm into C sine omega t. This is q. So our I will be equal to d by dt of this one, d by dt of Vm into C into sine omega t. So when you do this one, you will get I is equal to, it's a derivative you have to take. So you will get omega into C into Vm cos omega t you will get. Okay, see here, when you have the previous case, we had a minus sign. Here minus sign is not there. Omega C into Vm cos omega t you will get as the current here. But the voltage is sine omega t, and this current is cos omega t. Now you see here, this cos omega t can be written as, cos omega t can be written as sine omega t plus pi by 2. Previous case it was minus pi by 2. You have to remember that one. So here our I, or the current, is given by I is equal to Im sine omega t plus pi by 2. So our main point we got here, this Im, what is Im here? Whatever was coming before that sign. So that is Im. So Im is omega into C into Vm. This is Im. Okay, so let it be there. We will discuss about this Im later. We'll first discuss about this pi by 2. So here what happens? In the capacitor, the voltage is given by V is equal to Vm sine omega t. And what about the current? Current is equal to Im sine omega t plus pi by 2. So we can say in the case of capacitor, what is leading here? The current is leading. So that is very, very important. In the case of our inductor, voltage was leading. So for current, minus pi by 2 was there. But here current is leading. So that's what you have to remember as a most important thing in this one. In the case of a inductor, voltage leads and current lags. In the case of a capacitor, we have current is leading and the voltage is lagging. So you can see this is omega t and this is omega t plus pi by 2. So the angle is same only. There the voltage is leading by pi by 2. Here current is leading by pi by 2. And our Im is given by Im is equal to omega c into Vm. But actually our normal notation, if you take the case of Ohm's law also, what is current? I is equal to V by R. So this opposition should come in the denominator. In the previous case, it was like that only. In the case of our inductor, Im was Vm by omega c was there. Sorry, omega L was there. So there it was in the correct format. But here you see here, Im is equal to Vm into omega c is coming. So this format is having some problem. So we will make it in the same format like this. So what we can do? We can write Im is equal to Vm divided by omega c is coming here. So it will be 1 by omega c you can take. Now this is in the same format here. This current is voltage divided by opposition. Opposition means it can be resistance in the case of a normal resistor. Here we have reactance. As it is capacitor, we will call it as capacitive reactance. So we can write this one as Vm divided by Xc, where this Xc is called as capacitive reactance. So that point is very important. Xc is called as capacitive reactance. So what is this Xc? Xc is equal to 1 by omega c, which is called as the capacitive reactance. So you should remember in the case of this inductor, it was just XL is omega L, 1 by was not there. Here it is just opposite of that one. That is, it is 1 by omega c is coming. So what is the difference here? In the previous case, you remember we done a graph like this. So here omega was there and here XL was there. Now we have XC. So how it is? It is inversely proportional actually. XC and this omega is inversely proportional. So you will get a graph like this. We are getting a graph like this. That the meaning of that one is when the frequency increases, the opposition reduces. Once more, when the frequency increases, the opposition reduces. So what is the meaning of that one? When a DC is there, this capacitor will block DC. Capacitor will not allow the DC to pass through that one. But when AC is there or when high frequency is there, it can pass through the capacitor. So that is the most important difference between this capacitor and inductor when you are dealing with the AC. So when you connect a inductor, the inductor will allow DC to pass through that one and it will block AC or I am using the word AC and DC means DC is low frequency and AC is a little bit higher frequency. So this capacitor will allow high frequency to pass and it will block the low frequency. And what about inductor? Inductor will allow low frequency to pass and it will block the high frequency. Okay. Now here you see the waves for that one, how it is going. The voltage is like this and the current is leading. So current leading means you see how to draw this one. See here, this voltage reaches to maximum here and the current actually before an angle pi by 2 itself it reached here. So in this graph it will be here. Don't feel that this is behind. Actually when the time goes there, so first this one comes. So here the current is coming in front. I think that's clear here. Don't confuse voltage as going front here. Actually current is going front because time increases there. So first itself current comes. So here the current is leading, actually voltage is going behind. And here also you see the voltage is like this and the current is moving in front. The current is at an angle pi by 2 in front because the rotation is like this. Because omega t goes like this and the current is leading in front. So this graph also you should know how to represent this one. And you once if you remember the case of inductor, voltage was at the same position, but the current was this side. Current was here in the case of our inductor. And in the case of capacitor, it comes here. Okay, so once more, we have capacitive reactance here, which is a Xc, which is 1 by omega c. And the capacitor will allow high frequency to pass through that one and it will block the low frequency. That much we discussed. Now we have to think about the same way. We have to think about the power also. Here, what will happen to the power we have to discuss. So how we can see this power across the capacitor PC is equal to same way I into V, which is equal to Im cos omega t, this is current, into Vm sin omega t. So this will become Im into Vm cos omega t sin omega t. So this will become Im Vm by 2, same format almost, sin 2 omega t. So this is instantaneous power across the capacitor. Now we have to go for the average power. When you take the average power, you can see that this Im and Vm are constant, 2 also constant, that you can take outside, and the varying thing is sin 2 omega t, and its average, this value average will be 0. So here also power across the capacitor also is 0, just same as the inductor. So across the inductor we have the power 0, and across the capacitor also the power is 0. Both are same. That's why I don't want to waste time on that one, because already you studied all these things. So the power across the inductor is 0, power across the capacitor is also 0. Now we have to go for this all these things together, inductor, capacitor, and the resistor, all the three are together. Then what will happen to that one? Before that one, a general question is coming about the graph actually. So every time that same type question is coming, that's why we'll just discuss about that one. The question is like this axis they will not give, this opposition only is there, here omega is there, one graph is like this, and the second one is like this. This time sometimes it will be omega, or sometimes normal frequency f for nu they will give, and the third one is like this. So these are the opposition graph for 3 components. Okay, this will not go up. Okay, by mistake I done up. So like these 3 graphs for 3 components. The question will be to identify. For example, this is for graph A, this is B, and this is C. The question will be to identify this one. What is component A, what is component B, and what is component C, and some other details of the question. So if your identification goes wrong, means entire thing will go wrong. So here you see, whatever be the frequency, the opposition remains the same. So that will be a resistor. So in the case of resistor, it is independent of the frequency. Whatever be the frequency, it is independent of that one. Here you see here, when the frequency increases, the opposition also increases. That is high frequency, more opposition. So this will be for inductor. And this is for capacitor. When the frequency increases, the opposition reduces. So this will be for capacitor. I told you it will not go up. It will be like this. Okay. Now this is in the case of the opposition. Now if it comes in the case of current, this will remain same. But here it will become opposite. Because when the opposition is high, the current will be less. So it will become opposite. So you should be careful what is there in the y-axis, whether it is opposition or current. Based on that one, you have to answer. Okay, now we will go for a series LCR circuit. And if you have a circuit in which both inductor, capacitor, and we have resistor also, all these things are connected in series, then what will be the opposition of that one? Actually, that is an important circuit. Okay, so we will go in detail of this one. So this is an LCR circuit. So series LCR circuit means we have only series LCR circuit. If you are not using the word series also in your 12th standard level, only series circuit is there. So see here, we have a series circuit where we have a source of AC here, and we have L, C, and R. L means inductor, C is capacitor, and resistor R here. The first thing what you should know is, if you change this order, no problem, because no need of always drawing R here, C here. If R goes here or C here, because in series circuit, the current passing through everything is same only. So these all should be in a, that is the current should pass through all these things. So it should be in a circle or the square. What I mean to say is the order doesn't matter. If the capacitor goes here or inductor comes here, that will not make any difference. So we have a circuit like this. So here you can see, here we have 4 components. This is the only component which produces current, and here these 3 components across that one we will have a drop. So here we can apply Kirchhoff rule for this one. When you apply Kirchhoff rule, the voltage across this one is V, that is written here this side, and other three are drops, that is written the other side. So across the inductor, the drop is L di by dt, and across the resistor, the drop is I into R, and across the capacitor, it is Q by C. So this already we done in the previous case. All the things we taken together, that's all. So we have three drops here and one source. So this is the equation, that is L di by dt plus IR plus Q by C is equal to V. This is the equation for this circuit. For LCR circuit, we have a equation like this. Now, we have written an equation like this, but we should get a solution for this one. So when you go for a solution, we have two types of solution for this one. One is a solution which is just like a geometrical solution. We have a solution using phasor diagram, and we have another solution which is called as analytical solution. So analytical solution also may be present in your textbook, but it is not mentioned in your syllabus. Maybe new textbook it may not be there. So in other textbook it is there, but it is not mentioned in your syllabus. From the beginning onwards, only one solution is required. Okay, so don't worry about the analytical solution. We will go for the phasor diagram solution. So we have to use the phasor diagram solution for this one. And this phasor diagram solution also, actually it is a simple solution, but you have to concentrate on that one. Then only you will understand what is happening here. So we'll start with this graph. So what is this graph? That I will explain first. So we have L, inductor, capacitor, and the resistor here. And you know that through this one, there will be a current. So that current passing through all this circuit will be same only. So all the circuit, sorry. So all the components, there will be a current. So that will be in same phase. So because same current is passing through all these things. So that current will have a phase difference with the voltage. That's what we have to find out. So we will do this one step by step. So for that one, you see here, first I am drawing a phasor diagram like this. Now, you don't think about the total voltage and all. First you will think about the current, because current through this one is same only. So let that current be like this. So this is the current I. Now what is the source voltage? Source voltage is V is equal to Vm sin omega t. And what about the final current? Final current will be I is equal to Im sin omega t. This is not over, because in the resistor we have like this. And in the case of capacitor and inductor, one place we have minus pi by 2, another place we have plus pi by 2. But in this one, whether it will be minus pi by 2, whether it will be plus pi by 2, or plus some other value, that we don't know. That's why we will go for a random value plus phi. So what is this phi? This phi is the phase difference between current and voltage in the LCR circuit. So we have to finally we will get the value of phi. What is this phi? Based on this value of LCR and all. So phi is the phase difference between current and voltage. Now, what will be this angle? This angle will be omega t plus phi. Here, omega t plus phi will be the current here. So this is the final current. Now we will go for the voltage across each component. So the first we will think about resistor. So if a current is passing through the resistor with this angle and all, what will be the voltage across the resistor? You know one thing, in the case of a resistor, voltage and current are in phase. Voltage and current are in phase. So the voltage across the resistor will be in the same direction. So this is VR. So we got VR, that is voltage across resistor will be in the same direction. Now we have to discuss about voltage across inductor and voltage across capacitor. What about voltage across inductor and capacitor? Which one, in which case it will be leading? You know, in the case of inductor, the voltage leads. So if current is like this, the voltage across inductor will be in this direction. This is voltage across inductor VL. And what about voltage across capacitor? Voltage across capacitor will be lagging by an angle of pi by 2. So this is voltage across capacitor. Those who not understood, once more you listen carefully. The current through all the components is same. That's why we taken current like this. Voltage in the resistor will be in phase with current. There will not be any phase difference. That's why the voltage across resistor will be like this. And voltage across the inductor will be 90 degree in front or pi by 2 in front. So that we taken here. And voltage across capacitor will be here. So we taken it here. So we got all the three voltages here now. Now the thing is, this length of this one, what will be the length of this one? So this length of this one will be, this total length I am telling, this length will be VCM. Because voltage across capacitor, its maximum value, because when it comes here, you will get the maximum value like that. So this length, voltage, the length of this one will be VRM. And this length will be VLM. You have to remember this one. So this will be VLM. This will be VCM. So that is the length of this one. Okay, the magnitude of that one. Now you see here, this is a vector. This is vector. This is vector. All these things are vector. Now we have to get the final voltage. If you want to get the final voltage, you have to add this voltage, and this voltage. But these are in different direction. So in order to add this one, we have to add it like a vector. So we'll see how to add it like a vector. So this is the thing. So I'll draw it here, then only you'll get. So see here. First, our voltage across resistor, nothing to do. So that is VR here only. The previous one, it was a little bit this side, I think. Okay, no problem. Its length is VRM, which we discussed. Now, our value, if you take, this side we had the voltage across the inductor, and this side we had the voltage across capacitor. The actual value, if you take vector, these two you have to add. So one vector this side, another vector this side. When you add that one, the final result will be in the direction of the bigger one. See here, I am adding this one and this one. So when you are adding these two, actually this is, if you take this one as positive direction, this is negative direction. So the total resultant will be like this. So this one will be VC plus VL vectorially. But the length will be VCM minus VLM. I think it's clear. The length of that one will be VCM minus VLM, but vectorially it will be VC plus VL. Now you see here. So I am getting a vector here. What is this one? This is VC plus VL. And what is the length of this one? That will be VCM minus VLM. So finally, what we done? We had two voltages here, one this side and one this side. Now we simplified that one. We made it to one direction by adding these two. So one voltage is here. Here two voltage was there. We added that two and we got this one. But we had to add this also. And so we take this one to add means you have to use the triangle method. So this will be here. So this will be VCM minus VLM. So this one and this one, if you take, the resultant will be this one. Okay. So the voltage is here. So this will be omega t, and this one will be phi. I think you remember in the previous one, the total R will be omega t plus phi. So this will be omega t and this will be phi. And what about the length of this one? This will be Vm. Okay, so this is phi here. So this triangle is now our most important thing. Okay, so once more here, these equations you see here, Vrm will be Im into R. That we'll discuss later. And Vcm will be Im into Xc. Because voltage is actually current into resistance or current into opposition. So voltage across resistance will be, or the maximum voltage across resistance will be maximum current into resistance. And maximum voltage across capacitor will be maximum current into, instead of resistance, we have the capacitive reactance. So Im into Xc. And across the inductor, the maximum voltage will be the maximum current into the inductive reactance XL. Just B is equal to IR, same format only, you will get all these three. Okay, so we added this one and we got this one, and vectorially when you add, this is the final thing. Okay, so when you add first two, you are getting this one that you are taking here. And so actually, what is this one? This one, how we can represent? This is a triangle. So we can write VM square is equal to VRM square plus VCM minus VLM square. If you want to get VM, you can just take root of that one. So we are getting the value of this one. Okay, so that, see here. So what you are getting now? VM square is equal to, see previous value. Here, this RM is equal to IM into R. This all values we have to substitute in the next one. So what you will get? IM into R square plus IM XC minus IM into XL all square. Like this you have to write. Okay, so this IM is common. So you can write VM is equal to IM square into R square plus XC minus XL square. Or we will get IM is equal to VM divided by root of R square plus XC minus XL square. This is the format which we need. Why we need such a format? Because always we are using the same format. I is equal to V by R. This is the format which we need. So we got the current as IM is equal to VM divided by root of R square plus XC minus XL square. We got such a format. Now, what is this one? This one is coming in the place of resistance. Just in the case of inductor and capacitor, here we had this XC, XL and all. That was, we called that one as a reactance. Here we don't have the word reactance. Here we have another word that is called as impedance. So this value, we will write it as IM is equal to VM divided by Z, where this Z is equal to root of R square plus XC minus XL square. This thing is called as impedance. So when you have a inductor or capacitor alone, we have a opposition which is XC or XL, that is called as reactance. And when we have both capacitor, inductor and along with that one resistance also, the opposition is called as impedance. Many times that question came, what is the difference between the reactance and the impedance? So the thing is, if you have only capacitor or only inductor, we will use the word reactance. And if you have both capacitor and inductor, then we will use impedance. So this one is called as impedance. Okay, this Z value is called as impedance. Now, I think we are going with a little bit speed, but because already you studied this one and this is we are doing like a revision, that's why a little bit fast we are moving. So we have Z is equal to R square plus XC minus XL like this. This is called as impedance. That's what we did. Now you see here, if you take the previous slide, here we have a triangle. So what are the sides of this triangle? One side will be VRM, another side will be VCM minus VLM, another side is VM. If you want, you can divide all these things with I. So what will happen? This side will become Z, this side will become XC minus XL. Here it will become R like that also. So you just remember this triangle. This here angle phi is there, and this hypotenuse is VM, and this side is VR, VRM, and like this triangle. This one we are going to redraw again. So this is that triangle. So I told you why this triangle comes like this. Here, one more triangle I will draw that, then it will be clear for you. So this triangle like this. This side it was VM. This side it was VCM minus VLM. This side it was VRM, and this side it was phi, like this one triangle. Okay, we have a triangle like this. Okay. Now you see here. Here, if you take this triangle from this one, what is tan phi? Here you can see tan phi. This one you will get from this diagram. Tan phi is equal to here this side VCM minus VLM divided by VRM. So you will get tan phi is equal to this one. So the phi is the phase difference between our current and voltage. So we can get from this triangle what is phi. Phi is equal to tan phi is equal to this one, and the phi will be tan inverse VCM minus VLM divided by VRM, like that we can write. And one more type you can write as tan phi is equal to this equation is there, that is XC minus XL by R. How we are getting the same equation? Whatever equation we written for this one, the same thing we are dividing it with the current. When you are dividing it with the current, this voltage becomes XC and XL. Okay, so this equation we will use more. Okay, in more places we will write this one phi is equal to tan inverse XC minus XL by R. So we are getting this one from this diagram also. This is called as the impedance triangle or the impedance diagram. So this is this equation and this equation, whatever we written here previously, these two equations are very, very important in the case of numerical problems. Okay, so you should know the derivation up to impedance and this graph also, because based on this graph only we have to do some numerical problems. Most of the problems will come based on these equations. Now here this phi value is this one. We theoretically we done this tan phi is equal to this one. So here one problem is there, whether the current will be leading or the voltage will be leading. That's also, it is not told here, just phi value is there. This phi can be a positive value or phi can be a negative value also. Based on that one only we can say whether the current is leading or the voltage is leading. So you'll see that how we can say which is leading or which cases we have the phi is positive and which case the phi is negative. From the equation only if you take, you can see here, when XC is greater than XL, that is the opposition by capacitance is greater than XL, in that case the phi will be positive. Very, very important. So if XC is greater than XL, then phi will be positive. So phi is positive means what is that? Current and voltage, if you take, the phi is the angle of current, plus phi is for current. So the current is leading. I think it's clear. If XC is greater than XL, XC is greater than XL, in that case, what happens? The phi is positive. When phi is positive, what is the meaning? The circuit is predominantly capacitive. So that is very important. So in this total thing, this is given as an example, but in we cannot say in an LCR circuit whether current is leading or voltage is leading like that. We cannot say in general. It depends on the value of this capacitor and inductor. So if XC is greater than XL, then in that case phi will be positive and the circuit will be predominantly capacitive. And if it is opposite, that is XC is less than XL, then phi is negative, then it will be inductive. Or simply we can say the value of phi, that is whether the current is leading or the voltage is leading, that depends on the value of capacitor and inductor. So according to the value of capacitor and inductor, and this XC and XL means actually the frequency also is an important thing. So it depends on the situation, XC and XL value, whether the current will lead or the voltage will lead, that depends on that value. Okay, so this you should be thorough with this derivation and this thing. Actually in this entire chapter, the most important thing is this LCR circuit. So the LCR circuit and this diagram, that is the previous thing, the derivation and this impedance diagram, all those things you should study properly. And this one is not that important because this phi is positive or negative. So because if you end up by hearting like this and all, because in another situation this phi may be this side, so this will shift. So if a question comes, in that question to draw, you should know how much is the angle based on that one. Okay. So this one we cannot tell as such for LCR circuit. This is the graph. We can tell the graph for a inductor. We can tell a graph for a capacitor. But for LCR, it depends on the situation. Now we will discuss about one phenomena called as resonance. So in 11th standard also you studied about resonance. In sound chapter or in mechanical parts, we will study the resonance. What is this resonance? So we will first think about what is in general, what is this resonance. You might have observed in some situation, for example, if you have some engine working, for example, some old bus and or something, when it is going very fast, when it crosses a particular speed, most of the things from that vehicle will start vibrating. Now such buses may not be there, the old buses I am telling. So what happens is the engine is vibrating with a particular speed, and in the bus is having so much glass, so much materials, and all these materials, glass, everything will have a natural frequency. So when this frequency of the vibration of the engine matches with its natural frequency, the entire thing will start to vibrate. So that is one simple example of resonance. Or what you studied in 9th standard or in 11th standard, the swing which you are seeing in the park. You have a swing and a child is sitting in that one. So it is having a natural frequency. So for example, in 1 minute it comes 10 times. So it goes up there and coming like that 10 times it is coming. So you are pushing it. So if you want to continue the push or you want to continue it to swing, when it is coming 10 times, you have to push it 10 times. So if it is coming in 1 minute, it comes 10 times, you have to push 10 times. So the time interval will be correct. So your frequency of your applying force and the frequency, natural frequency of that swing is correct, then only it will have a maximum swing. And if that swing is coming 10 times in 1 minute and you are pushing 11 times, means your timing will go different. And if you do it 9 times also, it will go different. So what happens is that swing is having a natural frequency. If the applied frequency is same as that natural frequency, then what will happen? The amplitude will be maximum. So that is called as resonance. So in mechanics, if for every object there is a natural frequency. So when the natural frequency, the external frequency, applied frequency is same as the natural frequency, then the vibration will be maximum. That is called as resonance. Here also the situation is same only. When you have a LCR circuit, we have a inductor, we have a capacitor, and we have a resistor, and we are applying a AC to that one. So the current through this one, the current through the circuit will be maximum when this circuit is having a natural frequency, and if the frequency of the current which you are sending is same as its natural frequency, then the current will be maximum. That is called as resonance. So those who not understood resonance, once more I will tell you. For every LCR circuit, there is a natural frequency. What is that natural frequency? You will do later. For every LCR circuit, we have a natural frequency, and we are applying an external current to that one. If the frequency of the external source is same as the natural frequency, then the current through the circuit will be maximum. That phenomenon is called as resonance. So now we will see when it will be maximum, what are the conditions to be maximum. I think the resonance, what is resonance is clear. Those who not understood, once more I will tell you. For every LCR circuit, we have a natural frequency. If the applied frequency by the source is same as the natural frequency, then the current through the circuit will be maximum. That is called as resonance. Now we'll see here when it will happen. So I am taking here Im is equal to Vm by Z. This is the normal equation for an LCR circuit. So Vm is the voltage and Z is the impedance. So I will expand that one. Vm by root of R square plus Xc minus XL square. Okay, now this is the maximum current. Okay, the maximum, the current through the circuit will be maximum, means we are not talking about this maximum. This IM itself will vary according to that one. The maximum value of IM I am telling. Okay, don't confuse this IM and that maximum value. Now you see here, if you want to get the current as maximum, what is the situation here in this equation? If you want to get current as maximum, voltage divided by something should be maximum. So if you want to make it maximum, this denominator should be minimum. That is, Vm by this one, Z is Im. You want to make Im maximum, means Vm is a fixed thing and this Z should be minimum. So this value, that is R square plus Xc minus XL, should be maximum. Sorry, that should be minimum. Then only you will get Vm as maximum. So how we can make it minimum? So for that one, we are discussing about the frequency and how it responds to the frequency. So the resistance don't have anything to do with the frequency. Resistance will be like that only. What we can, what is depending on frequency is these two. So we will go for a situation. This value should be 0. That is this. We have R square plus something here. This R square we cannot change. It is independent of the frequency. This value should be minimum. That is Xc minus XL should be equal to 0. Then you will get a minimum value of this one, so that the current will be maximum. So Xc minus XL equal to 0 means Xc is equal to XL. And we have expansion of this Xc and XL. What is Xc? 1 by omega C. That should be equal to XL. So that is omega L. Now see here, this will happen for a particular frequency. So these two frequency cannot be different. It should happen for a particular frequency. That's what we are doing. For what frequency the current should be maximum. So the frequency at which the current is maximum, that is called as a resonance frequency. So both sides should be resonance frequency. So you will write omega 0 here. This omega 0 means it is resonance frequency. So you got 1 by omega 0 into C is equal to omega 0 into L. Now you can rearrange this one. So what you will get? Omega 0 square is equal to 1 by LC. Or omega 0 is equal to 1 by root LC. So this is our equation given here. So this is the condition for resonance. So this is called as a resonance condition. That is, already we discussed, resonance means when the LCR circuit is having a natural frequency, when the applied frequency is same as the natural frequency of the circuit, the current will be maximum. Now the question comes, what is that applied frequency? So its answer is this one, that natural frequency of that one is omega 0 is equal to 1 by root LC. So that is very, very important. So the natural frequency or the resonance frequency is given by 1 by root LC. Okay, now in this resonance, we have a graph here. This is the most important thing. So this one, see here in an LCR circuit, let us draw that graph in detail. That's why I'll erase this one. Okay, so now you see here, we are discussing about that graph. So this side is omega. It can be frequency F or nu, whatever you write that also. The omega is going toward this side. And this side is I. Actually, I am writing IM. Don't confuse this IM as this IM here. This IM means what? What is this one? This is the maximum current through that circuit. Okay. Because different frequency you are trying. So you see here, when you are trying different frequency, at a particular frequency, omega 0 or omega naught, at this omega naught, the current will be maximum. So that is here. So the graph will be like this. At that frequency, it will have a peak like this. Okay. So this frequency, this is called as omega naught. and we have a maximum frequency here. Now see here, this current depends on Vm by Z, and these two are 0. That's why we are this combination is 0. That's why we are getting Vm by R square is Im like this. Now you see here, if you change the resistance also, if you will get different graph. But you can see that if for different resistance, you will get different graph, but the maximum value will be same. So this is for a higher resistance, this is for a lower resistance. Okay, so that can come as questions for you. If this one is resistance is R1 and this is resistance is R2, which one is higher resistance, which one is lower resistance? Like that questions can come. So you should be aware of this graph. In general, this graph is very important. So this type of question can come. In a LCR circuit, the resonance graph is given here, and this first curve and second curve is given for two resistance R1 and R2. Which resistance is bigger? So you can see that when resistance is more, the current will be less. So that's all. Okay. Now this sharpness of resonance also was there as a topic previously. Now we don't have that one. Still, you should have some idea about that one. It should be very sharp actually. If it is very sharp, this will be too much selective actually. So we have some quantity called as Q factor and all. Now it is not there, but still you can think about such a thing. That is if it's a very good LCR circuit, it will be very sharp. Now, what is the use of this one? That's also very important. We have a LCR circuit and we have a resonance here. At resonance, we have the current passing through that one. At the resonance, we have the maximum current. Then why we are giving that much importance to this resonance and this LCR circuit? What is the use of that? So we'll go to the use of that one. You might have many uses there, and the simplest one which you can understand is if you take the radio. I will discuss not about the digital radio, the normal radio which previously people were using. In the radio, we have something called as tuning. That is, if you stand at a particular place, you will have so many radio stations there. You have 5 radio stations or 10 radio stations. So you have an antenna for the radio. So this antenna receives all the signals from all the radio stations, and this entire signal is coming to the radio. This radio have to select a particular signal from that one. So there, this one comes as an important role. I think you understood that one. That is, when the signal is coming, it will have all the frequencies. So we will adjust our inductance and capacitance in such a way that we are adjusting the value of inductance and capacitance in such a way that one second. We'll adjust the inductance and capacitance in such a way that this is very sharp like this. This one we can select. I think you understood that one. That is, we will have different capacitor. When you are tuning this one, we are physically using you are changing the value of capacitance in such a way that we will select a particular sharp value, so that only that channel will be selected. So when you change the capacitance, you have something to rotate there. When you change that one, what happens? You are changing the channel, different channel we are changing, so that you will get the different value of the this one capacitance. According to that one, you can tune. And you see here we have an inductor also. When you are changing the band from one band to another, then what happens is when you are changing the one band to another band, what we are doing is we are changing the inductor. So when you change the inductor also, we will have different value of this resonance. So this resonance is used for actually selecting that value. Okay, this resonance is used for selecting the value of that one. So simply you can say the resonance, the use of resonance is for tuning of the radio. So to select a particular channel, because so many channels are there, we have to select a particular thing. So we will use that one. So if you want to sharply select a radio station without mixing anything, so we need very sharp resonance. Okay, that's about the resonance. And the resonance graph is like this. Here, this is the current graph, And if you draw a graph for this impedance in the resonance, you will get just opposite shape you will get. So this side omega will be there, is this side. So it will be just opposite of this one like this. That is, the impedance will be minimum at that frequency. So you'll get like that. The impedance will be minimum at that frequency. Okay, so that's about this, our resonance. Now, we have to discuss about power in AC circuit. Okay. So this is also an important topic. We have something called as power factor. And so what is this power factor that we have to discuss here? So in AC circuit, how much is the power dissipated? Because across the inductor and across the capacitor, we already discussed. Now in a LCR circuit, how much will be that one? Or individually we'll go for inductor, capacitor, everywhere. What is the power that we'll discuss? Okay. So we'll start from the normal equation for the power itself. The power is given by power P is equal to V into I, which is equal to Vm sin omega t into Im sin omega t plus phi. Okay, like this. Okay, the power is this one, V into I, like this. We can write like this. So this phi value, we don't know how much it is. Okay, that is, phi is the phase difference between voltage and current. I think you got it like this, how it is, because V is this one and I is this one, and this phi value, it depends on resistor, inductor, or LCR circuit, that will be different. Now this power is given. Once more, those who not understood, we are calculating the power. Power is given by voltage into current. Voltage is Vm sin omega t and current is Im sin omega t plus phi. Okay. Now we are taking the product of that one. So this will be P is equal to Vm into Im by 2 into cos phi minus cos 2 omega t plus phi. Using the trigonometric identity, you can write like this. Okay. Now see here. When you take the power here, the average power of this one, here we have a t term here. So that value will become 0. Then the remaining value will be, P will be is equal to Vm into Im by 2 into cos phi. I think you understood that one. That is, we have the total this one. This is the instantaneous power. So this is having 2 terms. So you closely observe this one. You can see here also it is there, same thing. So here one is cos phi, and here it is cos omega t plus phi. So when you are taking the average value, where this t comes, t according to time it will change. So the average value of this part will become 0, but this part will remain. So that's why we are taking only this much. So P is equal to Vm into Im divided by 2 cos phi. In this one, time is not coming. So this will remain as a power here. Now see here, the power is Vm into Im cos phi. Now what I can do is, these two I can divide. So I will write it as P is equal to Vm by root 2 into Im by root 2 into cos phi. Vm by root 2 into Im by root 2 cos phi. Vm by root 2, what is this one? That is the RMS value. So power is equal to V into I into cos phi. So power is given by V into I into cos phi. Like that you will get V into I into cos phi. So what is important in this one? Generally, the power in the case of DC circuit is given by voltage into current, V into I. But when it came to this circuit, AC circuit, not only V and I, the angle between V and I also is important. I think you got it. That is, in a normal circuit, in a DC circuit, the power is given by voltage into current. But in the case of a circuit, AC circuit, not only V and I, this angle between voltage and current is also important. So this cos phi will change. According to the value of cos phi, the power will be different. So that's why this cos phi is called as the power factor. This cos phi is called as power factor. So this is very, very important in the commercial field. That is when we are purchasing electrical energy, when you are purchasing electricity from a company or whatever, for our school or for our home or for our industry, when you are purchasing the energy, electrical energy, this cos phi is very, very important. This power factor is very, very important. Now this is V into I into cos phi, like that also you can write, or I square R into cos phi, or instead of R in AC it will come, Z will come. I square Z into cos phi, like that also you can write. Power is equal to I square Z into cos phi, like that also you can write. Whatever you write, this cos phi will come in that one. So what is the importance of this cos phi? This cos phi is called as power factor, I told you. Now, the importance of this one is, you see here, we have a particular electrical connection to, for example, we think about our school only. For our school, we have a particular electrical connection. We are using so much of electrical energy to our school. Now, the power which is supplied to our school is P is equal to V into I. And along with this V into I, we have cos phi also. V into I into cos phi. And you know, the electrical power, when it is, this point is very important. Okay, you should listen carefully. This, when the power is supplied to our school or our institution, P is equal to V into I into cos phi, like that is there. The voltage will be constant. That is, we have a particular voltage connection. Our normal voltage is 220 volt, means we are getting a supply of 220 volt. So that won't change normally because our supply is 220 volt. Now what happens is, if this cos phi is not constant, how much should be the cos phi correct value? Actually, the cos phi should be maximum value, means cos maximum value, how much it can be? The maximum value will be 1. Cos phi will be 1. So the perfect value for this cos phi or the power factor is 1. So if the power factor is not 1, for example, this power factor becomes 0.7. If this cos phi becomes 0.7, what happens is, this voltage remains the same thing, same voltage that we already discussed. Once more, you listen carefully. We have to use a particular power. This power is given by V into I into cos phi. Now, this power which we require is a constant value. We cannot change that one. If the cos phi goes down, voltage also will not go down. Only thing is, to give the same power, our current should be more. That is, if the power factor is not 1, then to supply the same power to a particular place, we have to use more current. So when you use more current, what is the issue? If the current is more, what will happen? That, you know, if the current is more, for example, your school, the supply is coming from a particular area, for it, some 100 kilometer or 200 kilometer, we have the electrical supply line. So if the current is more, the heat produced is given by H is equal to I square RT. So if the current is very high, the heating effect in the electrical power line will be more. What we are paying for our industry or our school is for the power what we are using. You got it? So we are using 100 kilowatt. So we are paying for 100 kilowatt. If our power factor is less, to supply this 100 kilowatt, they have to use more current. So this more current is coming outside our campus. So that area, these wires will heat up. And for the company or for the government who is supplying current to you, for them it will be a loss because the wire is getting heated up. That's why for them, they will insist you to keep this power phi or the power factor as 1. If power factor is less than 1, the line will heat up and there will be a loss of energy, electrical energy. That's why everywhere we have to maintain this power factor as 1. So how to maintain this power factor as 1? That's another question. In most of the cases, this power factor will be less than 1 due to the lack of capacitors, because the capacitor and inductor should balance. This XC minus XL should be 0, like that you take it. So this capacitor and inductor should balance. Then only we can get this power factor as 1. So if that is not balancing, we have to add additional capacitors. So that is the main point. So if power factor should be 1, if power factor is not 1, transmission loss will be there. If you want to get if you want to reduce the transmission loss, we have to add additional capacitors. Okay, so that's about this power factor. And what is the value of power factor in different situations? What will be the power factor in resistor, for inductor, and for LCR circuit, and all we'll see now. Okay, so we will go for different cases of these power factors. So the first case is in the case of a resistive circuit. So if you have a resistive circuit, that is, you have a pure resistors only. Only one resistor is there in the, or no, I am not telling only just one resistor. Only resistance is there. There is no capacitor or inductor. That's the meaning. So if only resistor is there, means there is no angle between the voltage and current. So the current and voltage will be in phase. So the phi will be 0. So cos phi will be equal to 1. So the case 1 is in a pure resistive circuit, the phi is equal to 0, cos phi is equal to 1. So no issue at all. So we have the maximum power dissipation. So the maximum power dissipation will happen in a pure resistive circuit. Okay, in a resistive circuit, the power dissipation will be maximum, no doubt in that. Now the next one is case 2. If the circuit is purely resistive or purely capacitive. So if it is purely resistive, purely inductive or purely capacitive, so what will happen in capacitor and in inductor and capacitor? What happens? The phi value will be pi by 2. It can be plus pi by 2 or minus pi by 2. So when phi is pi by 2 plus or minus, what happens? Cos phi will be 0. Our power is equal to V into I into cos phi. If this cos phi becomes 0, the power is 0. So that is very, very important. That is the power factor in this one, inductive or capacitor. It is purely inductive or capacitive. It's not together. It is inductor or capacitor comes, means the power factor will be 0. So the power factor is 0 means what happens? A current is passing through the circuit, but no power is dissipated. That is a special case. That is, if you have a resistor, if the current is passing through the resistor, some power dissipation will be there. And in the case of a pure capacitor or a pure inductor, when current is passing through that one, no power dissipation will be there. Such a current is called as wattless current. So you can note that point. So what is wattless current? When current is passing to a pure capacitive or pure inductive circuit, there will not be any power loss or no power consumption will be there. The cos phi power factor is equal to 0. Such a current is called as wattless current. Okay, so wattless current means no power dissipation. Such a current is called as wattless current. Now our next case is about LCR circuit. In LCR series circuit, what will be the power factor? Same thing only. So cos phi is there. This phi will be, we already written that one, tan inverse XC minus XL by R. So based on that one, in LCR circuit, the power factor will vary according to the value of inductor and capacitor. Okay. So what is the value of inductor and what is the value of capacitor? According to that one, the power factor will vary. Now there is an important point. In the case of resistive circuit, there will be maximum power dissipation. If it is inductor or capacitor, there is no power dissipation. And in LCR circuit, how much power dissipated, that depends on the value of inductance and the capacitor. But in that case also, our power dissipation will take place only across the resistor. That is an important point. The situation is like this. You have a inductor, you have a capacitor, and we have a resistor here, and it is connected to AC source. And here, how much is the power dissipation? That depends on the value of this capacitor and inductor. Power dissipation depends on the capacitor and inductor, but the power is not dissipated across these two. According to the value of capacitor and inductor, the power is dissipated across the resistance itself. That point is very, very important. The power dissipated across a inductor and capacitor is zero in this case also. So in an LCR circuit, there will be power dissipation. This power dissipation depends on the value of capacitor and inductor, but it happens across the resistor only, not across the inductor and capacitor. Now, the power dissipation in the case of resonance. So when the resonance is taking place, what is the meaning of that one? The resonance taking place means this cos phi will be maximum, or the maximum this power dissipation will take place. So what happens to the power dissipation in the resonance means, simple answer, the power dissipation will be maximum at resonance. There also the power dissipation happens in the resistor only. So in LCR circuit, even if it is in resonance, if it is not in resonance also, every cases the power dissipation happens across the resistor only, not across the capacitor or the inductor. Okay. Now we have the last topic in this one, that is the transformer. Just we will discuss that one. So we have the transformers here. So you can see here, this is the picture of transformer. This is one and this is another. So these both are transformers only. Actually, theoretically, when we study transformer, we'll study this one. And these transformers will have some defects. To solve that defect only, we'll use that one. That we'll discuss at the end. So these transformers are a device which works based on mutual induction or electromagnetic induction. Transformers work based on mutual induction or electromagnetic induction. So now see here, this transformers works based on electromagnetic induction. We already told that one. Now, what is happening in this one, that we will discuss. So in this transformer, we have a coil here. This coil is called as the primary coil, where you are giving the supply. This transformer is having two coils. One primary coil where we are giving the input, and we have another coil here which is the secondary coil where we will take the output. This is called as the primary and this is called as secondary. And this one, what we are seeing in the blue color here, that is the core of the transformer. Generally it will be soft iron core. So we have a soft iron core here, and we have a primary coil and we have a secondary coil. So this primary coil, we will give the supply, and we are giving a AC supply to that one. So what will happen? It will produce some magnetic field. That magnetic field will be carried. That flux will be linked with the secondary using this core. So from the secondary, you will induce a EMF in the secondary coil. So you will get the power out. So actually, the purpose of this transformer is to increase and decrease the voltage. The transformers are used to increase and decrease the voltage by using the concept of electromagnetic induction or the mutual induction. And you should be aware of that fact that these transformers will work in AC only, not in DC, because there should be a varying current. So that is the answer for the question. Generally comes why high voltage AC is used for electrical transmission. Why high voltage is used in the current electricity, you might have studied high voltage. This transmission loss is inversely proportional, so that's why high voltage is used. Why AC is used? Because if you have to use these transformers for increasing and decreasing the voltage, that is possible only with the AC. For DC, we cannot use the transformers. Now, see here in this one, we have a primary and secondary here. Now you see here, the EMF across the secondary is given by the situation is like this. You have a current which is passing through the primary, and that produces a flux, and that flux is linked with the secondary, and some EMF is induced there. So this EMF across secondary ES is given by minus NS into d phi by dt. Our normal equation only, minus NS into d phi by dt, where NS is the number of turns in the secondary. Similarly, there will be a back EMF in the primary also. So the induced EMF in primary EP is given by minus NP into d phi by dt, you can write. Now you see here this secondary side, it is open there. So as it is open, the voltage and the this EMF will be same. So this one can be written as this is ES can be written as VS also. And now for the primary, you see here, in the case of primary also, this EP should be is equal to VP. If it is not like that, what happens is, because there is no resistance here, so if EP and VP are not same, means the current will be infinite current. That is not possible. So this should be same. So what we will get from this one, if you divide this one, very simple relation you will get. Vs by Vp will be is equal to Ns by Np. This simply we will call it as transformer ratio. So the input and output, the voltage ratio will be same as the ratio of the number of turns in the case of transformer. The ratio of number of turns will be same as the ratio of the voltage. So if more number of turns is there in secondary, then that secondary side the voltage will be more. So that's a type of transformer is called as the step-up transformer. So that is the primary number of turns is less and the secondary number of turns are more, so that the secondary the voltage will be high. So it is used to increase the voltage. Such transformers are called as step-up transformer. If you want to reduce that one, we will use transformers where the primary number of turns will be more and the secondary number of turns will be less. That is called as step-down transformer. Okay, now we'll discuss that one in detail. So this one already we written. Okay, this is equal to this much we already done. Okay, Vs by Vp is equal to Ns by Np. That we written that. Now you see here, if you think about an ideal transformer, what is ideal transformer? A transformer in which the input power and the output power is same. Actually, the transformers are not ideal. We will have some energy loss. Actually, we will do some numericals also in the next class tomorrow morning or something. We'll do. There are some problems on this one also. That time it will be clear, because after completion this theory part, I thought tomorrow morning we'll do the numericals on this one. Then we will go for the other chapters like electromagnetic waves, optics and all, and its numericals also we'll do. So here you see this ideal transformer means the input and output power should be same. That is IP Vp is equal to Is into Vs. That is, this is power in primary is equal to power in secondary. Power will be IP into Vp, that is current in primary into voltage in primary, which is equal to current in secondary into voltage in secondary. Okay. Now you see here, if you rearrange this one, what you will get? Vp by Vs is equal to, or Vs by Vp is equal to, Vp by Vs is equal to Is by Ip. That is, this voltage and current are just opposite. Where the voltage is high, the current will be less. So this equation we can add like along with that one. That is, Ip by Is is equal to Vs by Vp, which is equal to Ns by Np. So this is the simple equation for the transformer. You see here, listen here. Vs by Vp is equal to Ns by Np. That's the equation which we already had. So when you are taking I, it is just opposite. So once more I will tell you, in the case of a transformer, when the voltage is more, or where the voltage is more, there the current will be less. And the number of turns will be more where the voltage is more. So based on this one, we can classify these transformers as step-up transformer and step-down transformer. So first, if you take the case of step-up transformer, in the case of step-up transformer, what happens is, the voltage in the secondary will be greater than voltage in the primary. Same if the number of turns in the secondary will be greater than number of turns in the primary. And if you take current in the secondary will be smaller than the current in the primary. So the current into voltage, that product, that's power, that will be same in both sides in the case of a ideal transformer where the efficiency is 100%. If the efficiency is not 100%, then according to that one, change will be there. That we will discuss later. Okay, that's about transformer. So these all signals, these symbols will become opposite in the case of a step-down transformer. In the case of step-down transformer, this Vs will be less than Vp. Like that, everything will become opposite in the case of a step-down transformer. Now, your competency-based questions, the step-up, step-down transformer question can come, and they can ask you where it is used, where the step-up transformer is used and where the step-down transformer is used. That also can come there. Okay, so 1 second. So the step-up transformers are used to increase the voltage. So where it is used? So we have a power station where we are producing the power. So after producing the power, that power we have to transmit to somewhere. So just now we discussed the transmission voltage should be very high. So to increase the voltage to a high level, we have to use a high voltage. So in order to increase the voltage to a high level, we need a step-up transformer. So the use of step-up transformer is in the power station to increase the voltage. And now where the step-down transformer is required? Just opposite. This transmission line is coming to the city. In the city, we have to use the power for the normal houses to supply. There or in your school or in the industry, we have the transformer, that is step-down transformer. And again, we have step-down transformer in many other places. In our labs, we have the these eliminators where we will reduce the voltage, or we have the mobile chargers, or we have any such adapters, chargers everywhere where we will reduce the voltage. So in such cases, we have the step-down transformers. So step-up transformer and step-down transformer, the uses also is over, and this derivation and all things are there. And one more last point is there to discuss. Generally, what are the losses? We discussed that one, the efficiency, 100% efficiency may not be there. So what are the reasons for not getting 100% efficiency? The one reason is this flux leakage. So what is flux leakage means? We discussed now that one, we have a primary and secondary. So here some flux is there, and when it is going to the secondary, some flux will be missing. So that flux leakage means the entire flux in the primary is not linked with the secondary. That is called as flux leakage. So what is the reason for that one? The reason is the poor design of that one. So we can go for better design. The simplest way is the other picture what you see. That is, we have a picture like this. So the primary and secondary, we can wind one over the other. If you wind the primary and secondary one over the other, then the flux leakage can be reduced. That's one method. Now the next problem is the resistance of the winding. So we have the winding wire here. We are not considering the resistance of the winding wire. So the resistance of the winding wire, that is actually, it's in all the books, it is called as the copper loss. So how we can reduce that one? The best method is you have to reduce the resistance. How to reduce the resistance? Copper is copper only, we cannot change it. So only thing is you have to use a thick wire. If you use thick wire, the resistance will be less. So the resistance of the windings can be reduced by using a thick wire. And this eddy current is there. Now this, what is this eddy current? That is removed from the topic. Actually, eddy current is, in this one, some circular current will be forming in this thick metal block. Some circular current will be there. That is called as eddy current. So that will heat this core. So that is the eddy current. So due to that one also some loss will be there. So how to reduce that one? For that one also some method is there. So the method is, instead of making a very thick one like this, we will cut it into small pieces, and in between we will keep some plastic, or it is called as the laminated core. So if you use laminated core, we can reduce this eddy current also. And this hysteresis also, it is, what is hysteresis? That is not there for you to study. Still, we will tell that one. That is, when you change the polarity of this one, AC we are giving means positive, negative will change continuously. So once you change the positive and negative, here the magnetic field is coming. So that also should change like that. North-south should change. So it will not change that fast. It will remember little bit. Once it is made north, then it is changing to south means it will take some time. So that delay or that remembrance, that is called as hysteresis. So if you want to reduce hysteresis, only method is you have to use some materials which is having less hysteresis loss. That's all. So by using that one, you can reduce. Okay, so our time is over. So this entire things in this chapter we discussed. Only remaining is some question answers. So that we will do in next class tomorrow morning or according to the time we will do it. So for time being, we will stop it now. Thank you.